Welcome to this diagnostic field guide for interpreting optical tomography, OT, in laser powder bed fusion. Today we are focusing on real-time defect triage, the critical ability to distinguish between hot and cold spots as they occur on the build plate. Before we begin, if you want to stay at the cutting edge of industrial metal AM, please subscribe to our channel for more technical deep dives. The goal of real-time defect triage is to move from reactive inspection to a proactive, born qualified paradigm where components are qualified upon build completion. To do that, we must move away from reactive, post-build inspections like X-ray Computed Tomography because they represent a massive production bottleneck, often taking hours or days for large parts. Support structures alone can account for 48% of total manufacturing expenses, and their removal drives up to 70% of post-processing costs. For components with inaccessible internal channels, first-time right production via real-time monitoring is the only viable path to commercialization. Let's focus on the core monitoring capability that is optical tomography. It utilizes off-axis integration of near-infrared sensors to capture layer-wise thermal emissions. By using specific filtering to block the 1064 nanometer laser and plasma radiation, we isolate the thermal spectrum between 900 and 2300 nanometers. This provides a composite thermal image for every layer, offering high-fidelity insights into melt pool stability without the storage burden of raw, high-speed video. To interpret these maps, we analyze the gray value, which represents the integrated thermal emission of a pixel over the duration of a scan. A low gray value is a cold spot and indicates insufficient energy absorption, creating a high risk for lack-of-fusion porosity. Conversely, a high gray value is a hot spot and signals excessive energy input, which can transition the melt pool into keyhole mode or cause geometric swelling. A cold spot on an OT thermal map correlates directly to lack of fusion, LOF, porosity, found in X-ray CT scans. Physically, this occurs when the material fails to absorb sufficient energy to fuse with the previous layer, leaving behind unmelted powder particles. These defects are characterized by irregular voids with sharp, jagged edges, which act as severe stress concentrators. Practitioners should investigate 4 primary drivers for these energy deficits. These include spatter shadowing, where large ejected particles block the laser, plume interference from smoke and gas byproducts, dirty optics or soot accumulation on the laser window, and parameter drift, such as insufficient laser power or excessive scan speed. Hotspots indicate that the melt pool has become unstable due to excessive energy density. This often leads to keyhole porosity, where metal vapor recoil pressure creates a deep cavity that traps gas. In the OT image, this manifests as a spike in intensity that can lead to geometric swelling, potentially causing the part to protrude above the powder bed. The most common cause is the thermal insulating effect of the loose powder bed, which has only 5% of the conductivity of solid metal. Heat becomes trapped in overhangs and thin walls, leading to the inverted mushroom effect where the melt pool sags deep into the powder. Other causes include laser turnaround points where deceleration dumps excess energy and short scan vectors that prevent local cooling. Validation is critical for operational trust. Research using self-organizing maps and machine learning confirms that low OT cluster centroids map directly to physical voids found in X-ray CT ground truth data. This validates that in-situ thermal signatures are a reliable indicator for internal part quality and mechanical performance. Not every anomaly is a melt defect. Linear artifacts usually indicate hardware issues, such as a damaged recoater blade creating trenches or parallel lines in the powder bed. Similarly, transient sparks from spatter ejection should be ignored unless they begin to cluster persistently over several layers. The most important rule for an operator is persistence. Due to the self-healing nature of LPBF, the laser typically remelts 2 to 5 preceding layers, often filling small pores from the previous pass. An anomaly is only considered a propagating defect if it persists beyond this remelting depth, typically more than 3 layers. Context is everything when performing triage. An overheating signature is actually expected at downskin geometries due to the powder insulation effect. The real triage tool is comparing your live map against a golden batch or CAD simulation to determine if a hotspot is a normal geometric result or a true process anomaly. We are transitioning from mere detection to active correction with systems like Smart Fusion. These closed-loop controllers analyze sensor data and automatically adjust laser power in real time. By lowering power at detected hotspots, the system prevents dross and overheating before they compromise the build, allowing for lighter support layouts and better surface quality. To summarize your triage workflow, identify cold spots and check for spatter or optics issues. Halt if they persist beyond 3 layers. Monitor hotspots for dross and keyholing, especially near low-angle overhangs. Finally, watch for linear artifacts, which signal hardware noise like a damaged recoater. This presentation is based on foundational research into fuzzy machine learning, in situ monitoring of superalloys, and the physics of support-free fabrication. Thank you for watching. Please subscribe for more technical resources and check the description for links to the full papers and further reading materials to help optimize your manufacturing workflow.